I forgot to adjust it to go up there, and then I talked about stuff that you couldn't see.
Did you do it Algebra on Tuesday?
No, I did not. There was no help for us Tuesday. The unavoidable happened. Now we're all so sad about it. All right, let me begin with a word of prayer. Dear Heavenly Father, we thank you for this day, and thank you for these students. And I just pray that you'd help us to use this time wisely, Lord, to glorify you. In your name we pray, Lord Jesus. Amen. All right, so this is in fact the solution. I have not posted these yet, but I just worked out a few. I figured I'd share my thoughts on these initial homework problems because I have some solutions here. It won't take me too long to talk through them with you guys. I'm looking for my laser. Do you see my laser? Where's my laser? I got no laser. No, that's not my laser. Yes. Haha. Okay, so I hope a lot of people got this problem. This one wasn't too hard. To show that the center is a subring, you just got to show it's non-empty, so zero's in there. If you pick 2 points in the center, I gave it a name, I called it H. So you have xa equal to ax and bx is equal to xb for all x. So if I have the difference times x, then I get the different distributivity, but then they're in H, so I can commute them. And then I factor x out the other side. Consequently, a minus b is in the center as well. And likewise, I can push the ab past x using first the fact that b commutes with x, and then second, the fact that a commutes with x. And lo and behold, this proves that ab is also in the center. Sorry, I have juxtaposed the roles of a and x as I went from problem statement to problem solution, but I hope you can forgive me for that. Actually, even if you can't, I'm not erasing it. It was in pen. I wrote this in the car, I think it was, and I was just happy that it was relatively neat, so I decided to call it a day. I don't know, I forget where I wrote it actually, but anyway. Any questions about that one? I think, man, I sure hope if I put that on the test, I would sincerely hope that there are very few people who would not get it. Anyway, group of units in the ring. If it's a commutative ring with unity, that shows you that this is non-empty because the unity is itself a unit. So then if I pick 2 points in the group of units, that means that there is an x and a y in the ring such that a times x is 1 and b times y is 1. But that then means, of course, that a inverse is equal to x is also a unit because that's the condition to be a unit, right? So I also have that. Of course, I also have that xa is equal to 1 and yb is equal to 1. Being a little bit sloppy here, I guess I should also have those conditions. Anyway, this proves then that x is equal to a inverse, and so that we get closure under inverses, right? So if a is in the group of units, then the inverse is also in the group of units, and so it's closed under inversion. And I'm not saying that this is true. I'm saying that that's a guide. Okay. To suppose this is true would be to. I really shouldn't write this. What I'm trying to say is this is what I hope for. If I assume this from the outset, I'm assuming it's a group which is circular. So, but anyway, as I say here, that inspires me to try at yx for the inverse, since y is b inverse and x is a inverse, right? So, of course it works because b times y is 1 and then a times x is 1, so that proves that ab has inverse yx, right? Consequently, AB is a unit, and there you go. Now, I was about to say, okay, therefore by the two-step subgroup test, we got a group, but then it occurred to me, subgroup of what? No, I'm trying to establish a group structure here. I can't use the subgroup test. So what I've shown is I've shown closure under inverses, and I've shown that closure under multiplication. In other words, I've shown that multiplication is a binary operation, right? And by the way, we also know that the ring multiplication is associative, so we have an associative operation which is closed. In other words, it's a binary operation, it's associative, it's closed under inverses. We're given that the unity's in there, right? And what else do we have left? I think that's basically it, right? But also, it's a commutative ring, so this is also an abelian group, for what it's worth. So, stupid umbilicus.
Wait. Can you go back up?
So I was about to apply the subgroup test for U of R, but it hit me the subgroup of what? The solution is not that UR is a subgroup, rather it has a multiplication, which is associative, binary, with identity, closed under inversion, and in addition, it's unitive. Now, what are you asking me about?
The last time was just showing first. Okay.
Yeah. Of course, there is some room for confusion here, right? Because to show the multiplication is closed is to show that the product has an inverse. So there is some kind of like intertwangledness between the concepts. But that's just the definition of what it is. So. Now, what are the group of units? What are the group of units for the Gaussian integers? We can just solve through just straight calculation at the moment. So. So you're just looking to solve a plus bi times x plus iy equal to 1. So these are complex numbers. So I can divide. And I can conjugate. So then this is equal to that only if the real and the imaginary parts are separately equal. But these are integers. And these are integers. And those are integers. So you can't have a fraction equal to an integer unless this is what? That has to be 1 or... Yeah, right. Well, I guess my solution's got a gap in it too. I mean, couldn't it be that x is equal to 2 and this is equal to 4? I mean, excuse me. Couldn't it be, oh no, it can't I mean, I'm arguing right now why it can't be. Right, if x is 10, then this is automatically 100 plus something. So it's automatically bigger since x is an integer. Yeah, so there's the thing I didn't write down. As I said, we find, and if you look here, there's a little gap. But x squared plus y squared equals to 1. And so then this has to be 1, right? It's a sum of positive squared. Yeah. You got no choice. It can't be 0. That'd be bad. Right? So anyway, that's 1, which means that a is equal to x and b is equal to minus y. And then the question is, what does that mean? Well, but we're still stuck with x squared plus y squared equals to 1.
Yeah, that's making sense then.
And so if x is equal to 0, so what are the solutions to this in the integers? It's either one of these is 1 or minus 1, or the other one's 0, or this is 0 and that's plus or minus 1. There are 4 solutions to this equation. If you think about the unit circle in the complex plane, or wherever you want to think about it, if you think about the unit circle, just think about the unit circle in the plane, and think about z2, like z cross z. It's this grid of points. The 4 points which intersect the circle are 0, 1, 1, 0, 0, 1, minus 1, 0, and 0, minus 1. It's those 4 solutions, which you can also just figure out without graphical means just by thinking about what's possible. Anyway, if x is 0, then y squared has to be 1, which means y is plus or minus 1. And therefore, b is minus plus 1. This notation joins these things, okay? If x is equal to 1, on the other hand, that means y has to be 0. Likewise, if x is equal to minus 1, I should have just wrote plus or minus 1 here. It's too late, though. I couldn't fit the plus or minus in, so I was kind of stuck. So I had to write another sentence. Likewise, if my x equals minus 1, y equals 0. All of the awkwardness in my solutions can be attributed to me not being able to squeeze in another letter and or not having an eraser pen nearby, if you're wondering. So anyway, you got these 4 solutions. And if you think about what those mean as they relate, we're looking at a plus bi, right? So when a is 0 and b is 1, that's I. When a is 0 and b is minus 1, that's minus I. And then the other ones are like 1 plus I times 0 or minus 1 plus I times 0. Those are the 4 things. So basically the group of units in the Gaussian integers is this set. In fact, that's isomorphic to Z4. because you know I is an element of order 4. Multiplicatively. Question? Oh. This one's fun. In short, it is a subring. You apply the subring test to it. Difference, product, again in there. Bam, done. Oh, zero's in there, so it's not empty. Yay. This one is just annoying. Just annoying. Like, fine. If you accept this lemma, not too bad. All right? So if that's known, then you can just use the subring test. All right? But the question is, why is this true? And the nuts and bolts of why that's true, it's very much akin to proofs of the laws of exponents earlier in the course. I think so.
It's not just a big distributive property complete.
Well, if m and n are positive, m dot 1 is 1 plus 1 plus 1. And ultimately, it's because of the associative property of addition, or the inductive extension of that. It's not, it's not distributive, because n dot 1 is not a multiplication in the ring. N dot 1 is still defined even when n is not an element of the ring.
Okay.
Well, it seems like, well, something feels wrong about saying that, but anyway, I think maybe n still has to be an element of the ring if 1's in there, but oh, the thing is 1 doesn't have to be 1. 1 could be the identity matrix. And n dot 1 might be identity matrix plus identity matrix plus identity matrix plus identity matrix n-fold times. So it's not just it's not the distributive property, because n and 1 are different objects. It's not just multiplication of things in the ring. It's a notation for repeated addition. So yeah, that's the rub. And so basically, if they're both positive, then the difference is the difference of these number of 1s and that number of 1s. And that gives you 3 cases. Either it's just added together when m minus n is positive. It's 0 if they match. Or it's minus 1, minus 1, minus 1, minus 1, minus 1, minus 1 if m minus n is less than 0. In all cases, that's m minus n times 1, which matches this. And so they're equal. Yes. And that's just one of 4 cases. So yeah, then here's the proof if m is positive and n is negative. So we're adding together m copies of 1 and we're subtracting. But the subtraction is not this n, if n is negative, n dot 1 is actually minus n copies of minus 1 added together. Like this n times 1 is actually the sum L equals 1 to minus n of minus 1. It's repeated addition of minus 1 when n is negative. So you get this, and it's still true. And there are similar arguments for other cases. I'm just tired of this. I'm sorry, but I'm guessing none of you actually did this.
So you're saying that it's negative n 1 times, right? On that one, then why would you need both a negative 1 and a negative n?
Because negative, because n is negative, so negative n is positive.
Negative n is positive. Okay. Now I got you.
Yeah, if n were positive, then the sum L equals 1 to minus n would be a weird sum. Anyway, enough of that problem. Let's go on. This one is more fun. So this is the Boolean problem. So basically, game plan. First of all, skip this long and cumbersome argument. Let me show you my clean one down here. Again, but less. All right, there we go. So we're assuming we're in a ring with a squared equals to a for all a, and we just want to show that it's commutative. So I start by showing that since minus a times minus a is a squared, that means that by the property of the ring, minus a is equal to a. Step number 1. Step number 2, a plus b squared is equal to a plus b implies a plus b times a plus b is equal to a plus b, which implies that a squared plus ab plus b, a plus b squared is equal to a plus b, which is to say that a plus ab plus b, a plus b equal to a plus b, but to cancel the a and to cancel the b gives me ab plus ba, which is ab equals to minus ba, which is equal to ba, so ab is equal to ba, which is to say that the ring is commutative, and we're done. All right.
That was very distracting. I did not follow.
Oh, what was, my talking was distracting? Thank you. I was trying to auction off this problem, but to summarize, 2 things: show that any element's equal to minus the element, and then look at a plus b squared. Use distributivity. Use the reduction that a squared is equal to a, b squared is equal to b. Then things cancel. Yeah. The next homework. This one I enjoyed. A ring element's idempotent if a squared is equal to a. Prove the only idempotents in an integral domain are 0 and 1. An integral domain is a commutative ring with unity, no zero divisors, right? So first of all, easy picking. If you look at 0, is 0 squared equals to 0? Yep. So there's one possibility. If a is not 0, then, well, a is not 0. So suppose a is not 0 otherwise, all right? And think about this equation, a squared equals to a. Well, a squared is a times a, right? I should have written that down, sorry. Oh, I wrote it over here. And a is a times 1, so you get a times a is equal to a times 1 with a not equal to 0. But we're in an integral domain where we have the cancellation property, so we can cancel off the a's and we get a equals to 1. So either we have a equals to 0 or we have a equal to 1. That's it.
I think what I did was I subtracted a from both sides and then factored out an a by the distributive property. And then I had a times a minus 1 and then said that there aren't any 0 divisors.
That's what I did.
Very good.
I emailed you on that one asking you about that.
That's fine. That amounts to a proof of that's the proof of the cancellation theorem.
Okay.
Remember the proof of the cancellation theorem? We assume AB is equal to BC. I mean, assume AB is equal to AC. That implies that A times B minus C is equal to 0. But that must mean that either A is 0 or B minus C is 0 because there's no zero divisors. So if A is not equal to 0, that forces B to be equal to C. So your argument is exactly the proof of the cancellation theorem. So it's this one here could be very tedious. I would point out that the set we're looking at is a subset of the reals, right? Because D is an integer. I think that Galean intends D to be square free. Like, if D is equal to 25, then A plus B times the square root of 25 is A plus 5 times B. That is just a really weird way of writing the rational numbers again. So if D is a square, it's the rational numbers again. So it's a field. So to make it interesting, suppose D is not a square. All right? Now he doesn't say that, but he probably means that. I don't know. Maybe he intends what I just said. I don't know. I haven't talked to him. Where was I? Oh, my laser. So my point is it's a subset of the reals, so we can use a subring test to prove it's a subring, for one thing, right? So if you look at the difference of such objects, it's again such an object. If you look at the product of such objects, it's again such an object, right? Because you still have a rational linear combination of 1 and root D down here, right? Still a rational number times root D, still in the set. So by the subring test, it's a ring, right? It remains to show it's commutative because it's a subset of a commutative ring. It's got unity, right? The unity is 1 because 1 is equal to 1 plus 0 times root D, so it's in there. So it's unital. And then I just need to show that it's got an inverse for every non-zero thing. And I pull the inverse from the clear blue sky. Okay, not really. I just multiplied by the conjugate over the conjugate, you know. But this is the inverse, so we multiply it through and you get 1. This is legitimate because that can't be 0, all right? And moreover, so it works. There's still a looming question here. Why is the denominator non-zero? You might worry about that. I'll address that soon. Setting that fear aside, this is a quotient of things. If you look at this component and that component, they're both rational numbers again. So it's again in that. So anyway, it's every non-zero thing has an inverse multiplicatively. It's a field. Right? Commutative ring with unity such that every non-zero element has an inverse. It's a field. Now, you were worrying, some of you, that, how do I know that's in Q? Well, I know that's definitely going to be a rational number provided that this denominator is behaving. So suppose otherwise. If this is equal to 0, that gives me db squared equals to a squared, which gives me d is equal to a squared over b squared. Taking the square root of that, I get that the square root of d is equal to, and I'm assuming d is positive, okay? If otherwise, make it square root of minus d. Well, I mean, that's a good question. Was d positive? Oh man, if d is not positive, then I should have said this is a subring of the complex numbers. So sorry. I should have just used the complex numbers. It's safer. It's always in there, right? My bad. So I'll have to fix that before I post this silly thing. No one will see this, okay? So the square root of d is this, but that's impossible because this, unless it's a square, is an irrational number, and this is an irrational. This is a rational number. That's an irrational number, right? You can't have an irrational number equal to a rational number. These are just like, Clinton equals Trump. Doesn't work, Problem 93, the non-zero elements of Z3 adjoin I form an abelian group of order 8 under multiplication. Is this group, which one is it? So, you think about the possibilities. You got a 1, you got a 2, 1 plus I, 1 plus 2I, 2 plus I, 2 plus 2I, and then at some point it dawned on me, oh yeah, I and 2I is also there. I forgot about those. So my enumeration is always my own. Don't ask me where it comes from. I don't know. But then I counted 1, 2, 3, 4, 5, 6, 7, 8, and I said, I found all 8 of them. Woohoo! And then I just started multiplying things because we're trying to show whatever it is. You got to just pick on orders, right? If it's got an element of order 8, game over. It's Z8. Having looked at the back of the book, I knew that's what I was looking for. So 2 times 2 is 4. 4 is 1 because we're Z mod 3. So 2 has order 2. All right, that's nice. 1 plus I times 1 plus I. So I'll just stick that in my hat for later or whatever. 1 plus I times 1 plus I is 2I. All right, well, we're not done yet. That's kind of something. So then if I do 1 plus I times 1 plus I squared, that's 2I squared, which is minus 4, which is 2. Aha! 2 again. So I know that if I square this, I'm going to get 1. So 1 plus I squared is 2 squared. 1 plus I to the 8th is actually 2 squared, which is 4, which is 1. So 1 plus I has order 8. Therefore, it's the cyclic group, up to isomorphism, it's the cyclic group of order 8.
What does that phrase mean, up to isomorphism?
Well, it means that Z8 is a concrete thing we've defined, right? So like Z8 is a set of cosets of integers. It's 8z, comma, 1 plus 8z, 2 plus 8z, 3 plus 8z, right? Are these things those things? Well, no. 1 plus I is not a coset of integers, right? But there's an isomorphism that takes you from this set, this group of units, to those cosets of integers. So that's what I mean by up to isomorphism, is that the sets are, from the viewpoint of group theory, the same, but they may be in equivalent sets. They're different objects, but they have the same group structure. This one I'm not done with yet. There's your there's your zero divisor. What's my idea here? So it's not a prime ideal. If it's prime ideal, that means its quotient's an integral domain. That's the theorem, right? You know, ring mod a prime ideal gives us an integral domain. Ring mod a maximal ideal gives us a field. If you want to show that an ideal is not prime, one way you can do is look at the quotient by that ideal and show that that quotient's not an integral domain. What's it mean to not be an integral domain? Well, mostly we're looking for zero divisors. So here's a zero divisor. If I take 2 times 1 plus I get 2 plus 2i, which is in there again. This is 0 in the quotient, right? So there you go. Non-zero, non-zero. I think zero divisor, yeah. I guess I might worry that these are actually... I guess I haven't convinced myself that those are not in here. Are those not in there? I don't think they are. I should think about that some more, I suppose. Like I said, the solution's in progress. But anyway, there's a zero divisor, assuming I haven't tricked myself into thinking these are non-zero, right? So that's not an integral domain. Consequently, I is not a prime ideal by the theorem. There are 8 elements in this. How did I see that? I'm still working on this, but here's my picture. So basically the 2 plus 2i are the x's. So there's like 0, 2 plus 2i. There's minus 2, minus 2i. And the group of units in the Gaussian integer, we just figured those out before. If you multiply the generator for one of these ideal by something in the group of units, it doesn't change the... it's still in the ideal. That's a theorem we should prove. Thank you guys. That's something I've been searching for the words to say for a while now. And right in front of my face. But that is something we should prove. Expect a lemma here. But we did this before for my example in the notes. Like we took the generator of the ideal in the Gaussian integers and we multiplied by 1, minus 1, I, and minus I. That gave me sort of the 4 fundamental vectors to bridge off of in the picture. That was mostly right, except for the one wrong blue dot, which I still need to fix. But anyway, once I've done that, and I don't use color coding, so I've got to use something else. So I got x and x and x. I've got, I don't know what that is. It's a sun? Okay. I was thinking it might be a spinning turtle, but okay. I really don't know. But this one and that one are related in the same way that that and that are related. And you just count. So I've got 1, 2, 3, 4, 5, 6, 7, already counted it, 8, already counted it, already counted it. 8 things. The method, you take the generator, you find out all associates of the generator. We're learning next class what an associate is. An associate, 2 elements in a ring are associates if A and B are associates, if A is equal to B times U, where U is a unit. That makes A and B associates. So all of the associates to the generator will also be in the ideal. So for the Gaussian integers, that basically means you look at the element minus the element, I times the element, minus I times the element. It gives you 4 things. And then you just start building points which coincide to those 4 things summed. And if you look at that, you can sort of identify a fundamental cell, which is between the generators of the ideal itself. And then you just look for how many distinct points in it. That tells you how many different cosets there are. And then you can just add copies of add elements of the ideal to get all other points in the Gaussian integers. So once you pin down one fundamental region, you've found all the representatives.
How do you get from one thing to another thing? Like in the
1, 2, 1, 2. This is 2. plus 2i.
Oh, so it's kind of, instead of like having an x and y axis, that you're having a
Real and imaginary, yeah.
Oh, okay.
So I mean, this is my visualization of the Gaussian integers. It's my picture. Now this picture is not in Gaussian. He has paragraphs where he just sorts through. If you add this and this together, you get that. And if you add that and that together, you get that. So that's in the ideal, but that's not in the ideal. And if you blah, 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 blah. I mean, he's got like a paragraph where he does this like step-by-step analysis. Maybe there's an algorithm in there. I don't see it. It might be in there. I'm not saying it's not there. This is, for me, being a very visual person, this is a great way to think about it because I know when I'm done. How would you describe that with formulas? Not as pleasantly, right? I need some more colors, I think. Anyway, so I have bonus time today because I'm going to the CFA thingamajiggamajoo, so like I can talk to you guys for another 20 minutes at least. So that's all I got for solutions in here. I just want to show you guys these since I worked them out and stuff. So can I put these away? Cool. Thank you. Very helpful comment. So you guys bummed about Hillary? Yeah. Yeah, I'm really sad. Yeah, I'm really sad. I wanted to pay more taxes next year. And to be forced to go to a doctor that I don't want to go to. That was on my list of things I wanted to do. So guys, you might have questions. I'm not sure I have answers. Sure, which one?
That's what I'm trying to find here.
Did I assign number 8?
Is this, did you come out for tomorrow or later?
Just, yeah, number 8 on page 278.
No, it's 20, 40, 63, and 12 on 299 or 291. The rest are on these sections, 20, 40, and 63.
Nothing in, what chapter are we in? You're in?
So this is on this section here is 20, 40, and 63 on this chapter 15.
On 15? 20, 40.
And 63.
Ah, right. Let's do number 8. I bet that'll be helpful. Check this out. Prove that every ring homomorphism, if phi is a ring homomorphism from Zn to itself, all right? What do we get? Has the form, what's he say here? Phi of x, ax.
Squared is equal to A.
I guess from that other problem, if n is prime, it's an integral domain. So that means that the only ring homomorphisms are what? By the way, if n is equal to p prime, right? that means that ZP is integral domain. The other problem we talked about earlier. So a squared equals to a implies what? What does that say then? What are the possible homomorphisms from ZP to itself? It's kind of boring, isn't it? It's either a equals 1, it's the identity homomorphism, or it's the 0 homomorphism. Yeah. Huh. Sidebar. Anyway. So why is this true? I think it mostly has to do with the fact that if you look at x, right, it's equal to what? It's equal to x times 1, right? In other words, it's 1 plus 1 plus 1 plus 1 x times, right? So if I look at phi of x, right? I've got phi of x times 1, right? But it's a ring homomorphism, right? So that's phi of x times phi of 1, right? I don't know if that helps.
Phi of 1 is either 0 or 1.
Now, phi of 1 is either 0 or 1. How do you know that?
Well, that's off the sidebar where a squared is equal to a. So phi of 1 is a times 1.
Well, I'm supposed to show that, though. Well, but, I mean, phi of 1 times 1 is phi of 1 times phi of 1, right? Which is phi of 1. I mean, definitely phi of 1 equals to a, right? Has a squared equals to a as a necessary condition. I'm just having a moment's.
We're trying to
Oh, I'm an idiot. I'm an idiot. Look at this. Goodness gracious, guys! Don't let me get away with that. No, 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 no. I just talked you out of this belief, right? I mean, the way to think about this is not a product in the ring, right? It's repeated addition. So this is phi.
1.
Yeah, this is x times, right? In fact, I had a theorem I told you guys about where we put down two properties for ring homomorphisms, right? There was an additive and there was a multiplicative property. One of the additive property was what I'm about to write down. Phi of x times 1 is x times phi of 1. See, because this is equal to phi of 1 plus phi of 1 x times. Yeah. And there you have it. So this phi of 1 is the thing that's a, which has to be idempotent.
Wait, why is phi of 1 a?
Oh, I'm just calling it a. The point down here is, now this is, sorry, I need a different notation. I'm saying 1 times 1 in the ring, all right? I'm not using multiplication of the unity times the unity in the ring. All right? Ring homomorphism says that's phi of 1 times phi of 1. But of course, this is of course also just equal to 1, so this is phi of 1. So phi of 1 times phi of 1 is equal to phi of 1. And you see, right, I mean, we have this formula, phi of x, right? Is phi of 1, is x times phi of 1. Which it's commutative, right? So we can rewrite that as phi of 1 times x, or ax. Yeah. So that's number 8. Now the problem you guys had to work on,
Why did it matter that a squared equals a?
number 8 asks us to prove that. He said the question is, well, because that, I mean, I guess it doesn't, from some perspective, I mean, you could stop the problem here, so to speak, but it's much more interesting if we include this bit of knowledge, because that is very limiting as you search for possible ring homomorphisms, right? So like if I look for all ring homomorphisms, let's say from Z8 to Z8, I'm looking for all the solutions to a squared equals to a in Z8. Once I know those, every solution to that gives me a ring homomorphism by multiplication by that number.
Okay.
And this is not an integral domain, so there may be more than 0 and 1. 0 and 1 are still good, right? There's always 0 and 1. How about 2? Does 2 work? 2 squared is 4. 4 is not equal to 2. No, 2 is out. 3. Does 3 work? 3 squared is 9. Is 9 equal to 3 mod 8? 9. Oh, 9 is equal to 1. Yeah. Very good. How about 4? 4 squared is 16. 0. But 0 is not equal to 4. 5. 5 squared is 25. 25 is 1. 1 is not equal to 5. 6 squared. 6 is 36. 36 is equal to 4. 4 is not equal to 6. 7. 7 is 49. So, and then 7 is minus 1 is not equal to minus 1. 7's out. Huh. So it's just 0 and 1. Funny. Yeah. So Z6 has something more. I can't say. It's your homework, but you know. Anyway, I think this is extremely helpful for problem 20, what I've just done. Now Z20 to Z30, that's a different matter, right? How would you figure out homomorphisms from Z20 to Z30? Right. So a ring homomorphism, if you think about phi being a ring homomorphism from Z, let's say Z, what was my language before? I can't remember which one I put the N and where I put the M. Goodness gracious. I had that big problem that I wrote down wrong to start with, and then I corrected it, and remember? Yeah, leave me out to dry, aren't you? Let's see here. I know how it is. I'll find it. Just give me a second here. I think it's problem 72. I think so. I'm remembering 72. I could be wrong. Yay. Yeah, there it is. Any homomorphism from Zn to Zk, right? So if we go from Zn to Zk, right? A group homomorphism, right? I said, we proved in problem 72 that phi of x has to have the form what? Mx, right? Where what?
You say M or N?
M.
MX.
What's the condition on M?
Mod K.
What's that?
Mod K.
Well, yes, true, fair enough. I mean, mod K, yeah. But a lot of times we don't write that down. True though. Mx, K has to divide Mn is the thing, right? Now you guys are looking for ring homomorphisms, right? But at the additive level, this ring homomorphism is a group homomorphism, right? So this is the universe where you should look for possible ring homomorphisms, right? It has to be one of these guys. So if you're going from Z20 to Z30, or whatever it is, right? You got to look for M such that whatever it is, 30 divides 20 times, 30 divides, 20 times M. You know? But then more than that, you still have to respect the, the multiplicative part of the group homomorphism. So that will put further restrictions on which ones can actually be ring homomorphisms as well. So, anyway, other questions?
Yeah, 15, but that's like the same.
Yeah, well, I mean, once they give a specific one, then that I can answer pretty easily. It's the finding them all that I think is more challenging, yeah? I mean, oh, this one took a while, 15?
The homework problem.
Oh. Let's see. Determine all ring homomorphisms from Z to Z. Number 21. How would we do that one? Wait a minute, does that just fit into... See, this result was for Zn, wasn't it? The a squared equals to a thing. Was that really about Zn, though? I think maybe... I don't know. I mean, I'd be tempted to try phi of x equals to nx and see what happens. Is that a ring homomorphism? Certainly, if we have phi of x plus y, I mean, clearly it's into and well-defined, right? Okay. I'm here, I'm fixing an n for some n and z, right? Phi of x plus y, well, that's n times x plus y, which is nx plus ny, which is, looks like we're good there, right? Now, how about phi of x times y, though? I think we're in trouble there, aren't we? Yeah, see, I need that to equal to nx times ny for all xy, right? That implies, I think, basically by, I think you'd need n equal to n squared to get that for all xy, wouldn't you? So that means that n is either 0, 1.
That's it, yeah.
I was going to say or minus 1, but you're right. Minus 1's out. Yeah. Cool.
Why is minus 1? Oh, minus 1 equal 1, right?
Yeah.
Is that all of them, though, or could we find other things?
That's a good question. That, what problem was this? This is problem number 21. And which chapter are we in? zero map and the identity map. So let's see here. Yeah, I mean, you're like, well, you just wrote down a formula. How do you know there are not other formulas? I mean, that's a legitimate question, right? The thing is, we can again do that trick we did. Phi of x, right, is equal to phi of 1 plus 1 plus 1 x times. And so that's x times phi of 1. And I mean, I'm just showing it in the additive sense, but that extends to subtractions as well. There's a theorem in the notes that says the ring homomorphism. There's two things it has. The one thing is we have phi of n dot x equals to n dot phi of x. That's the additive content of the ring homomorphism. And then the multiplicative, we also have this phi of x to the n is equal to phi of x to the n. You get both of these things for a ring homomorphism. So that applied to the, I mean, basically you just apply this to fact that, well, let's say n times 1, right? So basically phi of n is equal to n times phi of 1. I was using x over here. I'm sorry, I've changed the roles of x and n again. My bad. But the point is that formula is general. It's forced upon us by the this property here. In fact, for any unital ring, you're stuck with this thing, aren't you? It's not just the integers. Anytime you've got a ring with unity, the formula for a ring homomorphism can be written as what? Well, okay, fine. Yeah, I guess I have to be careful there. Never mind. I can't say. I'm being too general. You know, if I can't do that for a matrix, right? I don't have phi of a, b, c, d is equal to what times phi of 1. You know, that's not true. I need to have a ring where I have the ability to reach other things by adding copies of 1. Not all rings have that structure. For example, the rings that are discussed in problems 11 or 12 in this section, you can't get to lots of things in those rings by just adding together the identity matrix repeatedly. Right. For example. You guys have other questions?
Did you do that if, like on number 11 there, if that was just a regular B in that bottom left corner?
What's the question about number 11?
Could you just add the identity matrix a bunch of times if it was just plain B in the bottom left corner instead of negative B?
I think if the B was 0, if I just had AA, I mean, if I, and I would also need that A wasn't a real number, but it was just an integer. So, yeah. So basically, if I have this as my ring, then yes, I can do it. Right? It's basically that's what we're getting to. So I didn't assign number 26. 26 is kind of fun. I think. I'm tempted to do 23 though. 26 seems fun though. We have Z cross Z mod principal ideal generated by A cross the principal ideal generated by B. We're supposed to show that that is isomorphic to, ring isomorphic to ZA cross CB. So this sort of thing, almost certainly we want to use the what? The first isomorphism, right? So what would you what homomorphism would you go for? You want a homomorphism which takes the thing downstairs as its kernel, right? I'm not sure I can do that. I mean, that's my knee-jerk reaction to this problem. What if I try phi of, let's say, x comma y equal to what? So in here, I'll map it to, I guess, just this and this, right? Which, of course, is just notation for x plus az, which is really just notation for x plus this and y plus this in our current notation, right? Those cosets. So, you know, is this here, phi is a mapping, right? It's a mapping from z cross z to za cross cb. We're defining it in terms of an integer. There's no well-defined problem here, right? X and y are specific things. There's no ambiguity there. What's its kernel? First, is it a homomorphism? Right? If you look at phi of xy plus, you know, x1, y1 plus x2, y2, is it phi of x1, y1 plus phi of x2, y2? Yeah, it's going to work because of the properties of coset addition. Right? So you can pretty easily show that this is in fact additive, and I'll do the multiplicative. Why not? So phi of x1, y1 times x2, y2 is, by the way, phi of x1, x2, y1, y2. Annoying double parentheses, equal to x1, x2 plus a, comma, y1, y2 plus b by definition of the map. But by definition of how you multiply cosets, that's x1 plus a, comma, y1 plus b times x2 plus a, y2 plus b. Because this is how we multiply cosets in ZA cross CB, right? By multiplying representatives. You can easily multiply these and get back to here, right? I mean, it's clear. Because x1 plus a times x2 plus a is x1, x2 plus a. But this is precisely phi of x1, y1, phi of x2, y2. So there you go. You'll forgive me if I don't write down the additive part, but it is additive, it's multiplicative, right? It's a ring homomorphism. What's its kernel? Kernel phi would be x and y such that, you know, x plus a equals to a, and y plus b equals to b, right? I mean, that's what it takes for this to be the zero, which is tantamount to saying x is in the principal ideal generated by a and y is in the principal ideal generated by b. So in other words, this is exactly a cross b, because x has to be in a and y has to be in b by those conditions. Right? You're fine. All that remains then, right, is to show that it's a surjection. But it's almost